My talk is titled OpenACC Unified Programming Environment for GPU and FPGA Multi-Hybrid Acceleration. So the motivation of this research is that we are considering to coupling the GPU and FPGA together for compensation with each other. So one of our big goal is that how to operate the big science based on the multiple physics, and or multi-scale. So in the multi-physics problem or simulation, there are multiple phenomena by the physics, and then like a thermal, electric, and magnetic or fluid dynamics, and so on. So problem here is that each of the element of the computation totally different or varies in some characteristics or behavior of the computation. Some computation is really SIMD style and suitable for GPU, but then another one is not so memory bandwidth bottleneck, but with some different conditional branches and not suitable for the GPU and so on. So I will show later about the FPGA. So one of our goals is that how combine the GPU and FPGA to compensate with each other for these different characteristics. And such a solution is finally, we think that one of the goal to attack the Amdahl's law problem, which is limited now by the strong scalability. So FPGA. So I think some of you are not so familiar to FPGA in today's HPC. So today's advanced HPC oriented FPGA is very, very good. So first, there are a lot of number of logic elements to implement the circuit. And we can use now the so-called HLS, high-level synthetic language, to like an OpenCL, not like a traditional hardware description language. And most importantly for the HPC, now the high-end FPGA is equipped with multiple channels of the up to 100 Gbps optical link. So that is very good because for the scalability of the computation, we can easily construct the FPGA own interconnection network. And there are some other good features. So the problem is that the programming and also some low standard of the flops, but we think that the absolute performance of the FPGA still not reaching to that of the GPU. So the goal and our strategy is that GPU and not using the FPGA for GPU, instead of GPU, but using FPGA with cooperatively using with the GPU. So this is a conceptual picture which we call CHAM. CHAM stands for Cooperative Heterogeneous Acceleration with Reconfigurable Multi-devices. So our concept is that how to combine the GPU and the FPGA together in peace to help with each other. So we have a CPU, of course, and GPU plus additionally FPGA here. So FPGA has two roles, computation and communication. And as I introduced, the FPGA today is equipped with a very high speed 100 Gbps multiple channel network. So we can construct the inter-FPGA communication link as well as the ordinary cluster network like InfiniBand. So we program the application to switch the part to part, which is suitable for the GPU or suitable for FPGA, but also some part is directly operates the parallel FPGA computation by this FPGA network. Well, this is a picture of our supercomputer named Cygnus. So Cygnus is the world's first multi-hybrid cluster with the GPU plus FPGA, which started operation in the April 2019. So we are operating this machine almost 1.5 years as an experimental big real cluster for the practical problem attack of the multi-hybrid computation. So there are in total almost 80 nodes and about 40%. That means that the 32 node is especially named Albireo. So I don't have a time to why it's called Albireo, but it is the actual GPU plus FPGA system. And all other nodes are equipped with only GPU. So every node has a GPU, but then 32 special Albireo nodes are also equipped with an FPGA additionally. So this is a block diagram of the Albireo node. We have 2 sockets of the Intel Xeon Gold and 4 GPUs. Each of them are NVIDIA Tesla V100. And additionally, 2 FPGAs, that is Intel Stratix 10 FPGA, one of the most advanced FPGA for high-performance computing. And we all have a 4-channel of the InfiniBand HDR 100. So in total, aggregated bandwidth is 400 Gbps plus FPGA. Each FPGA is also equipped with 4-channel of the 100 Gbps optical link. So it is very network gorgeous and the computation power gorgeous node. So this is the picture, and we have 2 socket CPU and the 4 NVIDIA V100 GPU and 2 Intel Stratix 10 FPGA. And on the back side, we have 4-channel of the InfiniBand HDR 100 and 8-channel of the 100 Gbps optical link from 2 FPGA, and finally the network switch, HDR 200, to make the full bisection bandwidth of the FAT3 to connect all the nodes. So as I told you that there are 2 kinds of the network. One is a InfiniBand FAT3 network as ordinary GPU cluster, and the other one is the FPGA original network. So since each node of the Albireo has 2 FPGAs, and we have in total 64 FPGAs spread into their 32 nodes. So we constructed the 8x8 torus network using the 4-channel of each FPGA. So we implemented some internal circuit to control the network and the router, and also the API or interface to connect the real computational kernel on here to the easy use of the application users. I have no time to explain about the network today, sorry. So how to program, that is the most important issue. So this is a picture of my most favorite monster named the King Ghidorah. That is an enemy of the Godzilla actually in the old movies. So we have this monster now because we have multiple GPUs, multiple FPGAs. FPGA has an optical link, and we have multiple CPU, many core, and also the 4-channel of the InfiniBand HCA. So how to program such a monster system? That is the biggest issue. So our solution is using the OpenACC in the high-level coding. So as you know, of course, the OpenACC is today's one of the very easy and effective way to utilize a GPU. But also there are several research-level compilers developed in the world. And one of the, I think the most famous one is Oak Ridge National Laboratories. Jeff Better's Future Technology Group provides an OpenACC compiler as a research compiler. So OpenACC goal is it supports multiple different devices. And most importantly for us, that it supports FPGA. And OpenACC compiler by Oak Ridge supports the OpenACC to OpenCL translator. And today, Intel provides the OpenCL to a real bitstream compilation for the FPGA. That is a real circuit implemented on the FPGA by the Intel SDK. So this compiler translates OpenACC to OpenCL. Then OpenCL is compiled to the FPGA by the Intel compiler. So we use these 2 background compiler. Another one is the PGI OpenACC, and currently it is replacing to the NVIDIA HPC SDK. But whatever, the OpenACC compiler for GPU, that is traditional. So we use the 2 kind of the compilers. So here we make some sort of the higher level total compiler, which is named MHOAT. MHOAT stands for the Multi-Hetero OpenACC Translator. So it is exactly aiming the CHAM concept, how to implement the OpenACC compiler in the CHAM concept. So it is a translator from the OpenACC, a single code to break into the multiple part, which is ready to run on the GPU and ready to run on the FPGA. So this part is translated to the two separate OpenACC program by MHOAT. And here we introduced our own programmer named the programmer ACC OMN. So it is not the ACC, but it is an extension with OMN. OMN stands for the OpenMP compiler, which is developed, Omni compiler, which is developed between the RIKEN and the University of Tsukuba collaboration. And here, on-device clause is the extension, and we can specify which device is to take care of this part of the programmer loop or something. So currently we support only the one GPU style and the one FPGA style, which is corresponding to the V100 and the Stratix 10. So user can easily code a program to control the multiple devices on the single OpenACC code. So this is a schematic view of how the compiler works, but it is quite simple. So there are three parts in the single OpenACC code: the host CPU code and the GPU part and the FPGA part. So the GPU and the FPGA can be switchable by the programmer ACC OMN on device, that as I explained it before. And MHOAT reading such a code and translate it into the different separated file for the two OpenACC compiler. This is so detailed detailed picture, so I will skip this one, but then it shows how finally the single program is separated and compiled and finally makes the single A.out file plus including the FPGA bit stream. Okay, so it is just a simple tiny program compilation example. So before the OpenACC unified MHOAT solution, we have a CUDA plus OpenCL solution, or maybe OpenACC plus OpenCL. So CUDA for GPU, of course, and OpenCL is for the FPGA. So we already make some application, practical one, running multiple devices, GPU plus FPGA on the Cygnus supercomputer. But here, I like to show that the CUDA plus OpenCL, of course, this is a combination of the two languages. And so many parts we must describe on the program. But it can be reduced about 44% in the count of the lines in the single OpenACC by MHOAT. And for the characters, it is much more. So we can reduce more than half of the code here. So that it is really good to easy programming for their application users. And most importantly, they must learn only one program code or program method, OpenACC. So currently we have some small fraction of the performance degradation on the MHOAT, but we are investigating what is the reason here. I will skip this one. So finally, I like to show that some possibility to apply the MHOAT. So currently we are developing the OpenACC code we named ARGOT. That is in the collaboration with application users of the astrophysics. And ARGOT's target is a very early stage universe. And there are a lot of light sources exist, and to make finally that first object of the universe, like the first stars and the first galaxy. And it is very complicated to match physical simulation. And we found that some part of the computation method inside the ARGOT is very suitable for GPU, but then other part is not suitable, and the performance is degraded about 10% of the suitable part. So we apply the FPGA computation here, and currently we have a very good result. So this is one example according to the several size of the problem. And when the problem size is small, the GPU doesn't work well. So here you can see that only the GPU computation and GPU plus FPGA computation, which lead us up to 17 times speed up. And when the problem size is increased, of course it's reduced, but still we have 1.3 faster performance with the GPU plus FPGA. Please remind that this is not an OpenACC, the traditional CUDA plus OpenCL, but this chart shows that the possibility or performance improvement by the OpenACC. So finally, I'd like to introduce an Omni OpenACC compiler now under construction by the RIKEN and the University of Tsukuba. And it is actually the OpenACC to OpenCL translator, something similar to OpenACC. But we want to implement all the heterogeneous multi-accelerator system from the original of the Omni OpenACC compiler. So we will implement our feature on this one. So this is a summary. So we are running the Cygnus supercomputer as the world first multi-hetero accelerating supercomputer with GPU and FPGA, and working for the high-level programming system of based on the OpenACC. And please remind the word charm here. Okay, this is my team, and they are very excellent, and we are ongoing of this research. Thank you very much.